So now we have the second example from the second lecture on strain. Here, instead of focusing on normal strain, we're focusing on shear strain. And what we're given is a system, it's kind of a sandwich of rigid glass plates that are 3 millimeters thick with nylon surfaces in between. So we have glass, nylon, glass, nylon, glass. And the glass we're assuming is rigid. It's given in the problem that we can assume that it's rigid because it's much stiffer than the nylon. So as a force gets applied from the side, and again, we're only quantifying the forces, the strains here, so we don't really care about the forces, but you could assume that there's some force up at the top pulling the top glass plate. The nylon is deforming as a result, and you can see that this used to be rectangular, and we're given that it deflects over 2 millimeters as a result of this load being applied. Now again, we don't care what the load is. All that we're trying to do is quantify the deformation by calculating the average shear strain in these two nylon layers. So all that we're asked for is the average shear strain in the nylon, and so we'll start our solution section over here on the right. Here we only have one thing to calculate, so we don't need to have subheadings. But again, it's always very helpful and expected to put the fundamental equation that informs the rest of your work for the problem. And here it's asking us for the average shear strain, and our equation for the average shear strain is that gamma is equal to 90 degrees or pi over 2 radians minus whatever the new angle is. It's called theta prime. So all of our angles start out at 90 degrees, and then our new angle, theta prime, could be larger or less than 90 degrees. And so what the shear strain is really quantifying is simply what is the change in angle. How much is it changing from orthogonal 90 degrees to its new deformed shape? So we could calculate it either way. We could calculate the new angle, or we could just figure out how much does it change from what we can assume was an original undeformed state, where the sides of each of these started out as vertical. So with that in mind, the only thing that we really need to figure out is what is the change in the angle. There's kind of two different ways to approach it for this. You could either look at the top layer or the bottom layer, or we could just take them and sandwich them together. The reason we kind of have to take both of these and sandwich them together and ignore the glass because it's not deforming is that we're only giving the overall deflection of both of these layers of nylon. We're trying to find the average for both of them together. We're not given that, well, this bottom piece of nylon deflects 1 millimeter, the top deflects 1 millimeter. Here we're just told the aggregate deflection for both layers of nylon. So I'm going to ignore the glass because it's rigid, and I'll draw a figure that simply stacks up the nylon one on top of each other. And so we know that just the nylon by itself has lifts or thicknesses of 5 millimeters. We also know that this distance here, the horizontal deflection, is 2 millimeters is given us in the problem statement. And so what we're looking for is there's two different ways to calculate it. One would be, well, what is this change in angle? It started out as vertical, now it's inclined at some angle. This angle right there would be what we would call delta theta. And I'll use a different color for that. The angle that represents the change from the original to the deflected is that angle right there. That's one way to calculate, the most direct way to calculate the shear strain. We could have also, if we wanted to, use this equation, pi over 2 radians minus theta prime, and this angle here in green, this is theta prime. You see, because the entire perimeter here is 90 degrees, and theta prime represents the final coordination, delta theta simply equals 90 degrees minus theta prime. Either way to look at it, there's often multiple ways to go about these problems. All right, so with that in mind, I think that the easiest way to calculate this is to calculate delta theta directly. And so I'm just going to represent this as a triangle right there. The triangle has a base of 2 millimeters, a height of 10 millimeters total. And so to calculate this angle, we simply use the inverse tangent. So all that I need to do to calculate delta theta equals the inverse tangent of the opposite side, which is 2 millimeters, divided by the adjacent side, which is 10 millimeters. And we get that delta theta is equal to 0.197 radians. And we know that delta theta is equal to the average shear strain, and so I can just say this is also equal to the average shear strain. So that's my final answer, and I will just say that the average shear strain is equal to 0.197 radians. Now, something else that we talked about in lecture 2 is that oftentimes with engineering systems we have a relatively small amount of deflection, rotation, things like that, and it usually makes it easier for us to simplify using small angle or small deflection approximation. And so I'll just give you an example of how that would work here. Here we said that delta theta is equal to the inverse tangent of the ratio of the sides of this triangle, which is absolutely true. That's the definition for that angle. But with small angles, small values of theta in radians, or delta theta in radians, for small angles, the angle itself is approximately equal to the tangent for small values of theta. So I could have also said that delta theta is simply approximately equal to the angle, the ratio of the sides themselves. So 2 millimeters divided by 10 millimeters. All right, saying the angle is approximately equal to the tangent of the angle. Again, this only applies to radians, that the angle in radians is approximately equal to the tangent. And this ends up being 0.200 radians. And you notice here the difference between using the inverse tangent and just using the tangent itself is very minor. It's, about 1%. So with that in mind, if you were to write on your assignment, note small angle approximation, that would have been completely fine to do for your homework assignment. Now you've got to be careful, and this just takes some practice, knowing what range of angles really allows a precise enough approximation to be used. Here we're talking about a very small angle. If we had 45 degrees, pi over 4 radians, you'd have a different value here. Much different than the 1 or so percent that we see difference here. But for relatively small angles, let's say lower than 0.25 radians, that should be a fine approximation.